Okay, so welcome everyone to this monthly Star Alice India webinar series. So we are delighted to have Professor Ralf Rapp from Texas A&M University for this monthly Star.
For this inverted sensors, which have CV measurement.
Rajendra, can you mute?
First.
For this monthly Star Alice India webinar series, the previous speakers included Professor Paolo Cubilino from GSI, Zhang Zhu from BNL, Peter Brown-Munzinger from GSI, Raju Venugopalan from BNL, Abhijit Majumdar from Wayne State, and Dinesh Srivastava. Professor Rapp did his PhD from University of Bonn, and then postdoctoral work at Research Center in Jülich and Stony Brook. After some brief stints at Copenhagen, Nordita in Denmark, and Stony Brook, he joined Texas A&M in 2003 and is currently professor at TAMU. He has received several recognitions, which included US National Science Foundation Career Award, Frederick Willem Bessel Research Award, Humboldt Foundation, and in 2014, he became a Fellow of American Physical Society. His top three exciting works included diquark boson condensates in high-density matter and instantons, chiral symmetry restoration and dileptons in relativistic heavy ion collisions, heavy quark probes of quark-gluon plasma at RHIC. All these are very, very well-cited papers in the field. Today, he will talk about a topic related to heavy quarks titled In Medium T Matrix Approach for Heavy Quarks and sQGP. So with this short introduction, I would now request Professor Ralf Rapp to start his talk, please.
Okay, good evening, ladies and gentlemen. Thank you very much, Bedangadas, for this very kind introduction. And it's indeed a great pleasure and honor to have the opportunity to share some of our research that we've done over really the last 10, 15 years. So let me go ahead and share my slides. And I will switch off the video in just a moment to optimize the bandwidth here. Let me go to full screen mode and oops, I think I should start from the beginning. I'm sorry. And let me also put up the pointer. I'm sorry. Yeah. There you go. Okay, good. So what I'm trying to introduce today is this what we call the in-medium T-matrix approach. It's really a rather generic many-body approach, quantum many-body approach that we originally used to describe heavy quarks to probe the properties of the sQGP, but then also asked really the question, how can we advance that to investigate the sQGP itself? And that will be sort of the logic along which I organize my talk. So I'll start with an introduction of sort of general nature. And then I will discuss how we can possibly construct an in-medium force, starting from the heavy flavor sector, how we can compute transport properties or transport coefficients with it, and do simulations for both quarkonium and open heavy flavor observables in heavy ion collision, and then come back to go a little bit deeper into what we can really learn from these studies about the QGP itself. Okay, so how do I get rid here of my video? I'm going to stop it now. And so let's start with the basics. Now the advanced. Oh, here we go. So quantum chromodynamics is in principle, well, the Lagrangian is well known, but the complication really lies in the coupling strength. And for that, you all know the famous running coupling, running with momentum transfer. It increases at decreasing momentum transfer along the distance. And the coupling constant becomes really large to an extent that perturbation theory becomes meaningless. There's essentially no convergence anymore. And indeed, we have good reasons to believe that qualitative new physics sets in terms of condensate formation. And this condensate formation then is what we, I'd say, believe, or to some extent already established, related to the sort of two main non-perturbative phenomena of the strong interaction, the confinement of the colored charges and the generation of hadronic masses from the originally essentially massless quarks in the Lagrangian. Now, a long-standing problem is, of course, what exactly is how do the forces look like that we encounter at long distances between the fundamental constituents? And maybe one of the best manifestations of that is if you go sort of in the static limit, so ask for the potential of force between two heavy sources, quark and an anti-quark, charm or bottom, even top. Unfortunately, top doesn't live long enough from bound states. But what we then find is in this limit of static interactions, in other words, no energy, only momentum transfer, that this perturbative sort of color-Coulomb potential develops into a linear potential as the manifestation sort of the non-perturbative physics. And indeed, I would argue up to today, even this linear potential is one of our best practical manifestations of confinement that we can observe indirectly, at least in experiment, because after all, this potential, which is now also very well confirmed from lattice-QCD, describes very well the spectroscopy of germanium bodymonus states, of course, with the extra complication that has come up in recent years of the exotic states. But this is a different talk. They often come in fact, at hadronic thresholds, and may well be also related to more of that physics. So this linear force indeed will play a key role in what follows. And in a way, what we expect is that these non-perturbative properties also are the key drivers of the phase structure of QCD matter here shown schematically as a function of temperature and chemical potential. And indeed, we believe that, for example, the quark condensates, which we have in vacuum, is indeed a key quantity that lets us to classify the phase structure. At very high temperature densities, we expect all condensates to be gone. But if you go, for example, at very high density but small temperature, there could be diquark condensates. And indeed, what we believe is that these condensate formations give us, with their inherent symmetry breaking, give us a guide of how to organize or better understand the phase structure. Now, being in the strongly coupled regime, well, first I should say, it is absolutely impressive how we can actually study systematically this phase diagram with heavy ion collisions over a really large part of it by varying the collision energy. And these studies, as you all know, have really provided us an enormous amount of information, among which maybe I would highlight at this point that what the kind of matter that we produce at high temperatures is by no means a weakly interacting gas, but much rather a strongly coupled liquid. And in a way, it is we expect that these transport properties, which are in fact near the lower quantum bound, should be tightly correlated with or related to the mechanisms, the non-perturbative mechanisms that govern QCD in the vacuum. And the purpose of the talk sort of is to try to elaborate a little bit this connection between, in particular, this confining force and the strongly coupled properties of the QGP. Okay, so we do have a lot of information also from first principle theory on QCD matter. Here sort of highlighted in terms of two plots, one for the bulk properties, the equation of state at zero chemical potential, which is well described by hadronic degrees of freedom up to a certain temperature, after which it then turns over and approaches that what you would expect for non-interacting quarks and gluons, but still is significantly below that. On the other hand, we have microscopic information on what is called the heavy quark free energy, which in the vacuum really is nothing but the heavy quark potential that I introduced earlier, here shown by the dashed line. But in the medium, it is not exactly the potential. In fact, that will be one of the key points later. But it is related, and we can use, hopefully, this information on how this free energy evolves with temperature, here suggestive really for screening, to understand better what the basic force is in the medium. So, and I should also say that even the free energy, which is sort of a lower limit for the potential, as I would argue, because you're subtracting this entropy term, that even at temperature, say, of 194 MeV, which is well above this chiral transition temperature, you see you're still well above into the positive, well above expectations that you would expect from a perturbative color-Coulomb potential, where you should be manifestly in the negative, even in the infinite distance limit. So bottom line here is, even at temperatures well into the QGP, there will be remnants of this linear force term left in the system. So the sort of questions we then want to ask more specifically to relate this to phenomena, the bulk properties and microscopic interactions, if you wish, is how can we indeed connect and maybe describe the bulk properties in terms of the underlying forces. Once we can have an idea what these forces are, we should be in principle able to calculate transport properties, in particular for heavy quarks, calculate their spectral functions, and in this way ultimately maybe also infer information about QGP structure, its spectral functions, and also its remarkable transport properties. Now, since this sort of potential in the vacuum is what I earlier introduced as being between two heavy quarks, the natural starting point to investigate its medium modifications is to go to quarkonia, and that was really the original proposition by Matsui and Satz in '86, to use quarkonia as a probe of deconfinement in heavy ion collisions. So what you generically expect is that the potential gets screened. The binding energy acquires non-trivial momentum and particular temperature dependencies, becomes smaller, so it becomes easier to dissociate the states. And indeed, dissociation is a separate quantity, if you wish, on top of the binding energy, and which tells you how quickly the states disintegrate in the medium. And the key quantity here is the width of the states. And that is indeed a basic transport parameter in the description of quarkonium transport. Now, for nature has been very kind to us in terms of giving us two heavy quarks, which we can, two types of heavy quarks that we can utilize in heavy ion collisions, the bottom and the charm quarks. And indeed, there's maybe only one state, namely the ground state, botomonia, the Y1s or eta B, which are mainly bound by the color-Coulomb force, while all the other states, the J psi and all other excited states, both Y and Charmonia, are mostly actually bound by the confining force. And that indeed corroborates this original idea that these states are excellent probes of deconfinement. Now, what we have to calculate to sort of make the, say, connection between, for example, lattice-QCD and experiment is quarkonium spectral functions. Here I show an example for the charmonium 1- channel. Of course, in the vacuum, I have the J psi, the psi prime, and then other states are actually above the threshold. And here's an example of a calculation of in-medium spectral function, which really suggests that as you go up in temperature, these states gradually dissolve. The psi prime is probably gone very quickly, But the JPSI, in fact, may survive quite a while into the QGP, and these kind of questions will be, of course, central to our investigations. Now, one thing to notice is that a key building block of understanding quarkonia in medium, such in particular as its width, which is basically how broad these spectral functions are, is governed by the interactions of the quarks within the bound state with the QGP, sort of shown by this diagram. While the screening essentially happens through the interactions between the quarks, but the widths must be due to interactions with the quark-gluon plasma. And then if you, in fact, if the bound state is not very strongly bound anymore in the plasma, which you expect, you can essentially take one quark away, and you see that the basic building block becomes that of the interaction of a single heavy quark, maybe a little off shell in the bound state, but the interaction of a single heavy quark with the quark-gluon plasma. And in this way, you could argue this is actually the simpler problem to first investigate this. These kind of processes, single quark interactions in the medium. And that then all naturally leads to the idea of using individual heavy quarks as probes of the interaction in the QGP and organization, really. So the nice thing, I mean, is that the heavy quark mass, both for charm and bottom, provides us with a large scale compared to, say, temperature in the system that allows us to make a lot of simplifications in the treatment of the interactions. For one, because the energy transfer is really parametrically expressed compared to the momentum transfer, radiation is really strongly suppressed, and sometimes also known as the dead cone effect in a way. And we are really dealing here with the analog of Brownian markers of our QGP fluid, really. The thermalization is delayed because the quarks are heavy, so it has to interact a lot of times before it reaches a thermal distribution. And this delay factor is just in the right, I would argue, just in the right ballpark where it is comparable to the lifetime in heavy ion collision. So we do not necessarily expect charm and certainly bottom to fully thermalize, and this means their spectra in the final state of a heavy ion collision contain a memory of the interaction history, and that provides a direct gauge of the interaction strength. In this way, we do have direct, rather direct, maybe even more direct than the than eta over S access to this diffusion coefficient. And on principal grounds, we should expect that, in fact, all the diffusion coefficient in the medium should be related to some extent, because after all, whether you're transporting, flavor or energy momentum or electric charge, at the end of the day, the carriers are, very much related, sometimes even the same ones, and thus their transport coefficients should be related. Which of course goes back to trying to find a common microscopic picture of the interactions that drive these transport properties. Now, key quantity are the scattering rates, obviously. Also in the Chamonia, these were the dissociation rates. For the charm, it's just or bottom, it's just the individual scattering rate, really. And scattering rate in a quantum mechanical context is nothing but a width, as I already argued before. And well, then you can ask the question, if these width or scattering rates become very large, at some point you might wonder whether the particles are still good quasi-particles. For the charm and bottom, we are probably safe, but what we can do, or what is in principle possible, is that if, for example, the diffusion coefficient comes out very low, I put here a number of, say, 3, then you can infer back the scattering rate, and that becomes very large, of order 1 GeV. So that is not far from the charm quark mass, and it's certainly much larger than what you expect for light quark masses. So if the light quarks then undergo the same kind of interactions, in fact, you would conclude that the light quasi-particles do not exist anymore because their widths are larger than their masses. So this is sort of the kind of information you can gain about QGP structure when you do these analysis of heavy quark interactions. Clearly, we need non-perturbative effects, as I said before. And the other nice thing about charm quarks is that they essentially produce in the early hard collisions of the incoming nucleons and then don't change their flavor quantum number anymore. So in particular, also through hadronization, they don't convert into other flavors. So basically, what you're dealing with at hadronization is you have a transported heavy quark distribution, and then it splits up into different hadron states. And that is, of course, a very nice tool to ask what are hadronization mechanisms. Okay, so with that, let me go into the next section and discuss in a little bit detail, hopefully not too much, the line of investigations that we pursued to get a handle on this in-medium QCD force. And the starting point here really is what we call the thermodynamic T-matrix approach, or quantum many-body approach, that from the many-body point of view is really a first principle approach. And it is formulated in terms of this in-medium T-matrix. You may know that cross-section is actually not well defined in the medium anymore. You cannot define in and out states very well. They're not asymptotic, but these amplitudes, they actually can be rigorously defined in the medium. And certainly you can recover the Born approximation in the realm of weak interactions, but that is not what we are dealing with here. So we have to do resummations of this interaction in this sort of what's sometimes called Lippmann-Schwinger series or Bethe-Salpeter equation, ladder resummation. And then you end up with an integral equation of the T-matrix where you iterate this V to infinite order. And that involves then an extra component, which are these propagators, the intermediate propagators of the two particles that are interacting, thermal propagators. And these propagators itself have to be resummed in what is called a Dyson equation. So the self energies, these in-medium self energies, are obtained again from the full T-matrix solution. So you realize then that you have actually a self-consistency problem because you need the T-matrix to calculate the self energies, and you need the self energies to calculate the T-matrix. But that is well known, in fact, also from nuclear many-body theory, but also other systems like cold Bose gases and so on. And it can be done usually by an numerical iteration procedure. Now, if you were to stick with the 4D version of this Bethe-Salpeter equation, that would be really quite challenging. But because of the large mass, as I argued before, the energy transfer in these interactions, so the energy transfer between these two particles, if you're involving heavy quarks, is suppressed parametrically, and you can do a reduction of the Bethe-Salpeter equation into a 3D, what is usually called Lippmann-Schwinger equation, and those can be really solved exactly then with rather standard methods. So you also realize then with the Dyson equation here and the Lippmann-Schwinger equation here, this is in fact one class of Dyson-Schwinger approaches. But the key problem is, what is this in-medium potential? Other than that, the many-body theory takes care of things, but you need this in-medium potential. So how can you get at that? In the old days, and we have also done that for many years, one went back to this expression for the free energy that you get from lattice with high precision. But the free energy is not really the potential. It's a combination of internal energy and this entropy term. But you can argue, though, that the internal and the free energy are limiting cases of the potential, where sort of F is the weakly limiting case, while the internal energy would be the strongly interacting limiting case. You can make some arguments around that with the entropy, which I wouldn't want to go into here. But the bottom line is you don't have to make these assumptions ultimately, because you can compute the free energy from the underlying many-body theory in terms of the spectral function sigma. The rest is just a straightforward integral. And what is the spectral function sigma? This is in this way of writing things in this sort of hybrid representation as a function of the energy, bound state energy, and its size, distance r. And it becomes indeed just the imaginary part of this two-body propagator, really, with involving the potential and then the self-energies of the individual quarks and the potential between them. So this is really the first principle, if you wish, connection between the free energy and the underlying potential, but you need also at the same time the self-energies. So the way to approach this problem then is to kind of reverse engineer what could be the potential so that you can describe the free energy with it. And to be able to do that, well, you use a trial potential as an input, say here a screened Cornell potential with a standard device screened Coulomb term and a screened string term, which reduces to a linear term once you go to low temperatures or zero temperature. But you also need these self-energies. So you have to dress up the quarks, as I described actually exactly in the previous slide. You have to dress the quarks as they interact and solve the self-consistency problem, and then calculate the spectral function, and from that the free energy, and in doing so try to infer the potential. And that is what is shown on the next slide. Before I go there, let me just say that if the imaginary part of these self-energies and of the potential is really small, then and so small that you can approximate this whole thing as a delta function, and you plug it in here. And if also the real parts are relatively small, because interactions are weak, then this delta function is essentially a delta function in the potential, and you recover the fact that the free energy is equal to the potential in the weakly coupled limit. So that is also in this equation, but large interactions as represented by the self-energies, in particular the imaginary parts, will drive away the underlying potential from the free energy. And that's why it's important that, especially for the strongly coupled case, you quantify this relation. And that's what we try to do, and shown here, in really carrying out this self-consistent calculation as I outlined earlier. And you actually find two solutions. You find two solutions. Both solutions describe the free energy well. That is part of the fit procedure, if you wish. These are these dashed lines, so they describe the lattice data for the free energy very well. But in a weakly coupled solution where the potential is rather weak, and also the imaginary parts of the quarks are relatively small, about 100 MeV or so, the underlying potential is actually close to the free energy. It's only a little bit larger at these low temperatures. On the other hand, you also find a strongly coupled solution, SCS, where the widths are actually very large, 600 MeV or larger. And these large widths then drive away the potential substantially from the free energy and get close, but not quite to the internal energy. So these kind of two solutions you end up with in this kind of approach. And then, of course, you have to decide, find extra pieces of information to decide which one will be the one realized in nature. And I'll come back to that later. At this point, I just want to sort of recapitulate that it is in principle possible to infer an in-medium potential based on this many-body approach, and using lattice data as the gauge. And you can go further using lattice data here for these Euclidean correlators, as they call it. These Euclidean correlators G, function of this Euclidean time, can be computed with very, very high precision in lattice, but it's not so trivial to extract a spectral function from those. However, if you have a spectral function from, say, a model calculation, then it's very easy to check how it compares to Euclidean correlators. And this is what is shown here. So for the germanium, bohdromonium, for various temperatures, the resulting spectral function here for the strongly coupled scenario can be used to calculate these correlator ratios relative to some reference correlator in the denominator. And you find a reasonably good, I would say, semi-quantitative agreement with this piece of lattice data as well. So you have some confidence that this rooting of this many-body theory in the lattice data within this potential or T-matrix approach, can be made sense of in a way. And maybe I should quote some numbers here. The J psi in this approach would melt this calculation at about 300 MeV, so indeed survive into the QGP. The 1s epsilon even deeper, while the 2s would actually dissolve a little earlier. Okay, so that was sort of the theoretical part, and now we're going into the application to heavy ion collisions by doing the heavy flavor transport both in the quarkonium and in the open heavy flavor sector. Although, as I argued, that's a little bit the opposite way, but it's actually how it happened historically, also starting from this original Matsuizat's paper, who made this brilliant suggestion of using quarkonia as a probe of confinement. So now this has evolved over the years, this idea into really quantitative transport approaches, mostly still at the semi-classical level, although quantum approaches are also actively being developed, and that should be done for sure to test the semi-classical approximation. So you can start from a Boltzmann equation for this quark distribution function, and in fact reduce it down if you want into a rate equation, which then becomes rather transparent because it involves two terms, namely the standard suppression term, but also once you have a state psi re-emerging in your system, then also the regeneration term will kick in. And that can be a range of temperatures where it acts, although in some approximations, you can say, well, maybe the most relevant point is at hadronization, and that is what is done in the statistical hadronization model, but it doesn't have to be just at hadronization. It can be throughout really the evolution of the system. A couple of comments on these key transport parameters. One being the equilibrium limit. That is what you should approach to. Every interacting theory should have, in principle, a well-defined equilibrium limit, and that controls the gain term. And that equilibrium limit, let me just say, is kind of it depends. The bottom line is that equilibrium limit for charmonia depends quadratically on your input charm cross section, because charm is produced in the early phases, and then you need a fugacity to keep it constant, and in the charm number constant, the subsequent evolution. That's where this, if you wish, chemical potential of fugacity comes from, and the J psi prime, and so on. Equilibrium abundances depend quadratically on it. That's why we heavily here rely on experiment to give you accurate numbers for CC4 cross section, and that is really has been made great advances recently by the Alice collaboration in providing us with an updated cross section, including which is a new sort of kid on the block, these heavy charm core, the baryonic states, which actually turned out to contribute quite a bit to this cross section. The other one is the reaction rate I mentioned before. There are various processes that have been investigated. Maybe let me not go into detail. At the end of the day, if the binding energies are not so large, it's really this sort of quasi-free, the scattering type of process rather than this dissociation, gluon dissociation, but it's really the scattering type of process which is a dominant one, and that there's this close resemblance to the heavy light quark scattering, really. I don't want to go into much detail, just give you some snapshot of or example of the heavy quarkonium phenomenology that has been developed over the years and how it compares to data. So this is these are the results for J psi production. And I should say, of course, you need to also treat the chi-c and the psi prime because they feed down to it. So they are also included in all of these calculations by the various groups. You see the main effect at RHIC is a suppression, although there are already contributions from regeneration, but they are relatively small, maybe half of this, or even a little less. But then you go to LHC and the RIA really kind of turns around and it's close to 1. And what was predicted really over the years before even the data came along is that there should be this dominance of the regeneration contribution coming up, and it was also predicted both by the statistical model and the transport models that this regeneration contribution should be really concentrated at low momentum, and also that seems to be very well supported by the experimental data. Now, within the same approach, in principle, you can treat bodemonia, shown here again for one sample from STAR, the other one, in this case, actually from CMS. And you see that the Y1S, it shows remarkable suppression, but again, one has to keep in mind that the 1S has about 50% feed down from excited states, and if the excited states here, the 2S and 3S combined, have a very large suppression. This is actually the main factor in also suppressing the 1s contribution. While at the LHC, the suppression of the excited state becomes even more extreme. There's relatively little or almost no regeneration, but in fact also the 1s now starts to see significant reduction. So our conclusions would be that the jet size starts to melt really at LHC energies and then re-emerge due to recombination, while the 1s still survives at some level without too much regeneration, really, because the bottom quark number is small, although this is highly non-trivial how that works out quantitatively. But the 1s still survives, and that is actually, I think, one of the good cases to go for even higher, collision energies in the tens of TeV regime to really see what happens to the 1s at even higher energy densities. So you can also plot that in terms of excitation functions, and say for mid-central, for reasonably central collisions, the shape size shows this increase driven by the regeneration contribution. The drag contribution doesn't really go that far down, but here one has to be careful because, for example, at SPS energies, we know there are very large effect from nuclear absorption, not related to hot matter suppression, which actually becomes smaller at higher energies because nuclei pass through each other very quickly and don't affect the jet size that much. But then, of course, extra thermal suppression comes in. And also in this calculation, there's still the bottom feed down, which comes in at a 10 to 15% effect. So just looking at this as the hot matter effect is not the right way of looking at it. And that's, in fact, the reason why it looks relatively flat. But in any case, you have this really telltale signature of the regeneration, and you don't have it for the botomonia. And so you really have a qualitative difference in their behavior, particularly the 2s, which is close in binding energy to the JPSI, very different behavior, right? In the here at the RHIC energies, they're still kind of comparable, but then the 2s goes down a lot, and at that level, even regeneration may become relevant, while the JPSI goes up. So that fits very well our understanding of this interplay of regeneration and suppression. So with that, I want to then move on to the open heavy flavor sector. And here I actually drew a little diagram because it's much simpler. If I were to draw this diagram for the thermonium, it would be a lot more complicated. It's in the backup slides, but I didn't even bother to show it. But for the heavy quarks, it's relatively simple. What happens to them once they are produced in these initial hard collisions? So of course, you need you can get the initial conditions for the time quarks from PP spectra, but there will be nuclear effects in principle there through partial distribution functions, for example, maybe Cronin effect at lower energies. And there will also be a short period of about a half a Fermi where the pre-equilibrium effects, including electromagnetic fields, possibly could play a role. But they are actually relatively small at the end of the day when it comes to the final modifications of the spectra. The main modification we still believe, after investigating this for about 15 years now, will be from the diffusion in the QGP liquid. Then, as you approach TC, you will have to somehow transit into hadronic states, and this hydrogenation process, again, a very strong interaction. It's not just a snapshot of converting from quarks into mesons or even charm baryons, but it's an interaction. And then we do believe that they're still on the level of maybe 10–20%, although that hasn't fully quantified yet, effects from the hadronic diffusion. One important point I think that I want to make here is that really there are no discontinuities in the interaction, and that I want to try to sort of indicate with these lines, dotted and dashed and then solid lines. So we're talking about a crossover phase transition and the interaction which ultimately binds the quarks into the hadrons here in the heavy quark sector. That force doesn't just go away. And in fact, I already argued from several angles why that shouldn't be, because the confining force, after all, we have indications just from looking at the lattice data that the confining force is present for a while, will survive for a while. The JPSI will survive for a while as we think into the plasma. So these confining interactions gradually set in, and then ultimately, when really the system becomes dilute enough from the quark point of view, you form a hadronic system, and then you change degrees of freedom. So there's bottom line here, in my opinion, there's no principal difference between the force that ultimately leads to the full hadronization and the force that provides these strongly coupled features of the diffusion and of the QGP itself, really. Okay, so then a few words on how we compute the transport. It's actually done in momentum space, although you do track the trajectories also in coordinate space. It is a Brownian motion, beautiful Brownian motion problem with essentially two transport parameters, the thermalization rate and the diffusion coefficient. Again, you need both of them because that's the only way that you approach equilibrium. Of course, if you go to very high PT, the diffusion is a small effect, and you're basically in the quenching regime, and then just this first term will do essentially. But at low PT and intermediate PT, you need them both to make sure you approach equilibrium. And both of these coefficients, momentum, diffusion, and thermalization rate, or at the fundamental level related to the heavy light quark scattering matrix, two-body scattering matrix element, weighted with this extra angular factor, which makes it a thermalization rate and not a scattering rate. So the scattering rate is larger because it counts every scattering. But for thermalization, you need a few scattering, actually quite a few, to thermalize the heavy quarks. Of course, the thermalization rate is related to the relaxation time. It's just the inverse. And there's this very important Einstein relation between the two coefficients to make sure that you're really reaching equilibrium limit. So their ratio actually quite nicely gives the temperature beautiful relation. So that's what you have to calculate in terms of these scattering amplitudes. And you also have the relation to the spatial diffusion coefficient, which is essentially the inverse of the relaxation rate at zero momentum. So that is something one should keep in mind. This ds, the diffusion coefficient, is the zero momentum limit. But of course, in experiment, you're never dealing with exactly zero momentum. So actually, the momentum dependence of this thermalization rate is also something very important that we need to understand. And ultimately, we would have the hope that these transport coefficients are related. In fact, at the end of the talk, I'll come back and come back to this relation and argue that this coefficient actually has very important information in it. Okay, so quick look at the charm light quark T match. It's not so different from the tape side. They melt, so these D mesons, if you wish, they melt quicker. But as you go close to CC, there will be these strong D meson resonances, and those are really essential drivers in accelerating the thermalization rate roughly by a factor 10 compared to perturbative interactions. Also, it is nice to see that if you do this in medium potential approach, that as you go down in temperature close to TC, you do recover what you expect for the vacuum D meson mass. But this is, of course, just a consequence of that your potential model, if you wish, already works in the vacuum reasonably well for these states. So these resonant interactions really drive the interactions. And although the parton density increases a lot when you go, say, from 200 to 400, the parton density in the QGP increases by a factor 10, roughly, right? 8, say 2 to 3 or so, maybe more. And while the relaxation rate here in this calculation only increases by a few percent, and the reason is because there's the compensation between increasing density in the medium and decreasing interaction strength. And so at the end of the day, in this strongly coupled solution, which are the solid lines, these do not very strongly depend on temperatures because of the build-up of the very large interaction strengths at the parton density drops toward TC. In the weakly coupled scenario, you're much closer to perturbation theory. It's still a factor 2 or 3 larger, but especially close to TC, there are huge differences between those two. Okay, so then let me show this figure of the diffusion coefficient, the zero temperature limit of this, zero momentum limit of this gamma or A coefficient, we sometimes call it. And so here's shown what you get in perturbation theory. It's about 30. Then you see what you get with the weakly coupled solution when you're close to the free energy. It's about 10. And then in the strongly coupled scenario, where it's really small, below 5 for most of the part of the temperature evolution. And you also need hadronic evolution, and probably this one is not the final answer. There are more recent calculation by the Valencia group, very nice many body calculation, much along the same formalism, T matrix formalism than we use on this side, they've used on that side, and it actually can come down. And so of course we believe it should be continuous, but you know, the values we're talking about are really, really small. And indeed, all these values of 3 or so, and if you go back and check what this implies for the collision rate, it is on the order of 1 GeV. If you do an explicit calculations, I mentioned before, it's maybe not quite 1 GeV, maybe 600, 700 MeV. But if you're really making the statement that this is the diffusion coefficient that you extract, then you're making the statement that in the light sector, there are no quasi-particles anymore, right? Because the widths are just so much larger, or comparable or larger than the masses in the light sector. So this has dramatic implications, in other words, for QGP structure. Okay, so a couple of words on the hydrogenation. Now, fragmentation is, of course, what happens, well, in what used to, you know, let's say in E plus E minus collisions, but probably also in PP collisions. In the IPT, this is still, you know, the major player in town, although as a recent, there have been discussions whether also in PP, you know, at the LHC, there could be a recombination, which I think is very possible. But then in the medium, you know, there are lots of light particles around, and recombination becomes a serious player, maybe even dominant player. And what I wanted to emphasize here again is that this is really an interaction. It's not just a projection of quarks into a hadronic wave function. There's much more to that. Often in coalescence models just do that projection into a hadron wave function, but it's much more than that. It's really an interaction that forms a resonance, right? In that sense, we have actually developed this resonance recombination model where the recombination is sort of a resonance scattering into a hadron, and you just don't let the hadron decay anymore, but then after the formation, you move on with the hadron, so-called resonance recombination model, which is in principle based on that same scattering matrix that you use as a function of temperature, as I just showed. And again, the confining force here is probably the main agent in the heavy quark sector, which facilitates this hadronization. Okay, so then you can do analogy with it in a simulation. Before I go into detailed comparisons with the experiment, let me just again demonstrate what happens in a strong versus a weakly coupled scenario. So here at the level of the charm quarks, let's focus on the V2, because the V2 turns out to be the most sensitive gauge, in fact, of the interaction strength. And what you see that at the quark level, say all the way to a temperature of 170 MeV or so, with a strongly coupled solution, you generate decent V2, about 10%, but with the weakly coupled solution, you factor, 4 or 5, 3 or 4 down. So the weakly really does justice to its name. It's too weak to generate any substantial V2 that could do justice to experimental data. Also remarkable is that the internal energy and the strongly coupled solution seem to give rather similar results, at least at local T. You go into, you carry it to the data here without any hadronic diffusion. You see the weakly coupled, even though you get a big boost from the recombination, also in the weakly coupled scenario, you still factor 2 to describe these actually very nice data by both ALICE and CMS. So you can really make a case that diffusion coefficients, which are sort of at the level here even of 10, which is this weakly coupled solution, is far from what you need to do justice to this beautiful data. So here a more comprehensive look at the data. RHIC on the left panel, ALICE, LHC data, ALICE and CMS on the right. Upper panel are lower panels V2. And you see you get a really decent description at this point. Although I will say that these calculations that were carried out by Min He do involve still a K factor of about 1.5 on top of what we have right now for our strongly coupled solution. part of that is that we didn't include radiative energy loss, but there's also a part in the low energy regime which there still seems to be some missing strength in our calculations, and we have some ideas where it could come from. One is, I mentioned already, the improved hadronic diffusion calculation by the Spanish group, which we hope to use at some point. And there are also some other types of interactions that we're investigating, that could provide a little bit more strength. We have to see about that. But if you buy for the moment that K factor just for phenological purposes, you see that you get a good description, and also this splitting up of the different hadronic states after you come in with a charm quark close to TC. It's a universal charm quark distribution, but the same charm quark distribution gives rise to these different hadronic states, lambda C, ds, and d0. And even in experiment, there seems to be really a difference there, and that tells you a lot about the hadronization mechanism, namely that indeed recombination, say with two quarks instead of one, or recombination with strange quarks, which are enhanced in the QGP relative to say PP collisions, that all plays a role and channels into the observables through the recombination process. That's really quite beautiful, and we are very much looking forward to improve precision in these lambda C and ds data that can really do a great job of informing the theoretical interpretations. Okay, so last 5 or 10 minutes, I want to come back and ask questions after all these efforts of developing this D-matrix approach for heavy quarks, and then doing transport with it. Really a program of 15 years by our group alone, but there are many groups in the world doing that. There are also some very strong groups in India doing that. And this is all needed to really form collective knowledge and in search of agreement and common ground in the approaches. There have been several large-scale efforts, rapid reaction task force, the JET heavy quark working group, and also recent Trento workshop, again another one in the fall, where the groups get together and try to really find common ground. Now, after all these efforts, at the end of the day, you want to extract properties of the QGP. So, and here's an attempt where we try to do that using still that very same formalism, but now being a little bit courageous and applying this sort of potential scattering also in the light quark sector and calculate from that then the equation of state. So now we're also doing light, quark-gluon, gluon, quark-antiquark, and even quark-quark interactions between light particles, calculate the free energy, the equation of state, really, that's the pressure. And how we do it is in this self-consistent, what is called Luttinger-Ward quantum many-body theory. You calculate the one-body Horton propagators from the self-energy, and then the self-energies are calculated from the T-matrix. And really, the point here is we're using that very same potential that we use for the quarkonia and the heavy quarks with relativistic corrections. In fact, they are already included play actually already a role for charm quarks. Now they're, of course, very important. So these relativistic corrections are included, and then there are these color factors. So we're really summing up all possible color configurations, right? Quark antiquark, not only color singlet, but color octet, and then quark would have a triplet and anti-triplet and sextet. Then in the gluons, you get even more. So all the color projections, and in fact, also angular momentum states are accounted for. But other than that, really the same potential we used before, but then implemented into this many-body formalism. And then there's one last freedom we have, that is sort of the input quark masses that right now, in principle, should still come from a condensate, or possibly, but that information we haven't gotten to yet. So these are sort of our fit parameters for the equation of state still. And what will play really a key role is this, what is called the Luttinger-Ward functional, which includes interaction contributions. So you see here the pressure, the first term is really the sum of all the medium constituents with one body propagators. But this phi, that includes the interactions. It's written out a little more detail here. It involves self-energy, it's closed off with propagators against all these fancy resound diagrams. So that's what the interaction contribution is. It is included here with the full width information. So this is not a mean field calculation. This includes the full spectral width of the spectral functions and self-energies in the process. It was quite some calculation that actually former PhD student finally completed after the work of all the previous sort of generations of students. And here's what we come up with for the equation of state. So the black are the lattice there. We can fit the equation of state. That's not really the achievement here because we have two masses, quark and gluon masses at hand. You know, you can fit the equation of state. The quark-gluon masses are on the order of half GeV for quarks, 1 GeV for gluons. So that's not the achievement. The point is how this this pressure really is composed in terms of the quark contribution, the quasi-particles, if you wish, and the interacting contributions. And what is shown here in the dashed line is this Lagrange word, this phi functional that is essentially driven by the quark, by the interacting contributions. And in fact, you can look at the spectral functions that enter into these calculations at the 1 and 2 body level. So at the 1 body level, the quark spectral functions here at high temperature, you have a reasonably well-defined peak again. But at low temperature, it's extremely broad. In fact, it's very broad here, and it has some collective mode on there. So it's very broad at small momentum in the quark sector. But then you go in the two body level. At high temperature, there's not all that much left. It's really the same as in the D meson channel we looked into before. But at small temperature, close to CC, you build up this large rho resonance. What is it? Actually, it's a rho omega resonance, right? We don't have pions yet because of the chiral physics, but this is the rho resonance, you know, that builds up. And you know, this is exactly what dominates the degrees of freedom. At high temperatures, 400, the degrees of freedom dominate by broad parton distribution functions, and the width actually suppresses it from its Stefan-Boltzmann limit. While these partons become so broad that their contribution at small temperature drops down, and it's taken over by the hadronic contributions from these resonances that form. So really, in a way, this calculation shows there's a transition in the degrees of freedom from partons which melt into hadrons which emerge as you approach TC. We can't go all the way down yet because we don't have all the chiral physics under control. And, you know, also, so there are some issues to be overcome going even lower, but I think already at this level, it's rather promising. So the last slide then is going back and calculating the transport coefficients, not only the ds, which I said before, which I discussed before, but now also the eta over s from the light degrees of freedom, as figuring in this description of the equation of state. And so let me this is the last slide before the conclusion. So let me walk you through this plot here. So here again, in blue, we plot the results of the weakly coupled scenario, and in red of the strongly coupled scenario, both for the ds solid line and eta over s dashed lines. So, okay, you know, for the strongly coupled scenario, the ds in units of pi t and eta over s are close to the quantum bound, which we believe is probably around 1. So close to the quantum bound, this is the ds we used before, the eta over s here, also quite small, quite consistent with what you extract from hydro calculations. That was very nice. And then for the weakly coupled scenario, you know, the eta over s is not all that different. We were surprised ourselves, but the ds is really much larger. And so the eta over s, not all that, okay, it is a factor 2 larger, but not all that much larger. So then what we did is we took the ratio of the ds over eta over s in this dimensions units. And it turns out that this ratio actually, when you look through the literature, has a very distinct value in the strong and the weakly coupled limit. In the strongly coupled limit, you know, these are essentially 1 and the ratio is 1, you know. But if you go into the perturbative calculations, you find that the ratio of these is actually 5/2. It's actually 5/2. So that ratio of the 2 pi t ds and the 4 pi eta s. If you use perturbation theory, this ratio is 5/2. So this gives you now a quantitative handle to really make an assessment of whether you're in a strongly coupled regime or not, right? Because if the ratio is 1, that's what the strongly coupled regime predicts. If that ratio is 5/2, that's what weakly recoupling calculations find. And then you take the ratios for the weakly and strongly coupled scenario, and you indeed see and that was by no means trivial. Could be a coincidence, of course, but the strongly coupled scenario, although we're not all the way down there at 1, the ratio at low temperatures is close to 1, suggestive for a strongly coupled system. And it keeps rising, it starts rising then at high temperatures, while the weakly coupled scenario is around this 5.5 throughout. So it seems we really have a measure of what strongly and weakly coupled means when we put into context the heavy quark and the light quark sectors here from these calculations. And that we found quite exciting. And that was sort of my main conclusion on QGP structure, and brings me to my conclusions. So I discussed today a T-matrix approach that we use to describe macroscopic many-body physics of the quark-gluon plasma constrained by lattice data, and we deployed it to heavy flavor transport. But then also, after all these very hard work and investigations of heavy flavor transfer, came back to ask what are the implications for QGP structure. And if I were to sum that up, I would give you these 3 bullets. So there will be the confining force that will survive above TC. And this long range force, as you go down toward TC, will melt the long wavelength quasi-partons. Those partons will melt very broad. At the same time, the confining force builds hadronic states explicitly. And in this way, it also generates the long wavelength properties of the QGP liquid, resulting in these very small transport coefficients. And last but not least, I argued that this ratio would be a measure of the strongly coupled nature of the QGP. So that is it. Sorry, I went a couple of minutes over time. Thank you very much. And I very much look forward to some questions.
Thank you. Thank you, Ralf, for this very nice talk. So I already see there is a raised hand, Partha.
Okay, thank you. Very nice talk. So I have one general question. So you talked about this RAA, the nuclear modification factor, as an observable to measure suppression. But presently there are some arguments that RAA is not a good observable to look for Charmonia suppression, because the production dynamics is, so instead one should look at hidden to open charm ratio. So what is your take on that?
I'm sorry, the RAA you were referring to Charmonia or to open charm?
No, I said when you talked about this Charmonia suppression in terms of RAA, so how good RAA is an observable to look for Charmonia suppression? Or one should look at hidden to open charm ratio, where the shadowing effects generally can.
Okay, I see. Yeah, that was something Helmut Satz suggested. Yes. Yeah, I don't have a strong opinion on that. I think if we have the open charm cross-section under control, and Alice has done a fantastic job on narrowing down the uncertainty, then it doesn't really matter if you normalize to that cross-section, because you know that number, and if you divide by a known number, you don't really gain new information. So I'm not against this ratio, open over hidden, hidden over open charm, but I don't see a whole lot of benefit as soon as you have the charm cross-section under control. But who knows? I mean, sometimes these ratios exhibit interesting features that are not easy to see if you don't plot them. Let me just say that at the end of the day, the part of the problem is, and I think that's maybe also what this is aiming, the charm cross-section. If you just were to divide by the charm cross-section from the PP measurement, then the RAA would have no extra information, because the denominator would also just be the charm cross-section, which scales with the number of collisions. I guess the point is that this charm cross-section can undergo shadowing, and then the denominator and the RAA would change, and that would give some extra insights. But again, that would require that you know the charm cross-section in AA. And that is certainly, currently beset with this uncertainty of the shadowing. And we're looking forward to explicit measurements of low PT lambda C in particular, say, to narrow down also this cross-section in AA. Yes, thank you.
Okay, thank you. So Vedanta, can I ask one more?
Okay, go ahead.
Trivial one, maybe a very trivial one. So you said that for epsilon 1s, it is the binding potential, it's basically Coulomb, whereas for other, it is the confining part. For Jepsa,
Yeah.
is it because of the size argument that since it is very small, say the Coulombic part dominates, and for others, it is the confining part dominates?
Yes, I fully agree with that. Yes, if you go to the, if you go to this Cornell potential in a vacuum, and the epsilon 1s is maybe a size of typically 0.2, then you're starting to get here into the Coulomb well, right? But really all the others, Jepsa and so on and so forth, they're typically at 0.5 or more, and their wave function is really spread along this linear part of the potential where the Coulomb is already small. Yes, absolutely. That is, I think, a correct argument.
Thank you.
Okay, Anirban?
Yeah, thank you. So you showed the calculation where you calculated the V2 of D mesons compared with the data with weakly coupled, weak solutions, strong solutions, and with U.
Yes, yes.
What was that U? Because that describes this D meson array absolutely, I mean, bang on. I mean, what is that U? Is the internal energy part of the free energy? But what is there?
Okay, so U is the internal energy. So if you go back to,
yes,
if you go back here, if you solve that for U, you see U is a very large potential because you move that entropy term on the other side. So basically, what you're saying is, if you have extremely strong interactions, then the timescales are so short that the entropy production doesn't play a role, and you should take out the entropy term out of the F, and then you're left with the U, right? The F, that's also sometimes a source of misunderstanding. The free energy is a competition between the free energy is a competition between minimizing the energy and maximizing the entropy. That's just thermodynamics, right? Mm-hmm. So if you want to eliminate the entropy term, because entropy needs a little time to build up. So if you have very fast interactions where you don't have time to build up the entropy term, you should take it out and you're left with U. This is sort of the absolute upper limit you can imagine for the strength of the potential. And unfortunately, I don't have plots for U, but I can tell you the U, if you were to plot the U potential here, it would be even higher than the strongly coupled potential, or especially also at higher temperatures. So the U potential in the old days, not that old days, was a proxy for the strongly coupled limit if you just had this lattice data available, right? The lattice data could give you the U, and many groups, including us, used U as the upper limit for what that potential could be. And that is what these calculations are corresponding to. We have been using for quite a while, actually, for at least a decade, we have been using that U as a proxy for the internal, for the potential, right? And yeah, this good agreement here, I would put in the realm of accident or coincidence.
Okay.
I wouldn't read too much from it. In any case, you would have problems with the V2 here. So yeah, that's an interesting observation, but yeah, could be a coincidence. I don't know. I mean, yeah, I cannot say more than that, really. Mm-hmm.
Okay, yeah, fine.
Thank you.
Vedanta, can I ask one more?
Yeah, sure. Go ahead.
Thank you. The plot where you showed the primordial and the regeneration, the part separately and the total, where you showed the charm in as a function of not this one. There is another
energy. This one.
Yes, this one exactly. Yeah. So for JSI, you argued something about this primordial. It's not being flat. Can you please say it? It was.
Yes, thank you for giving me the opportunity. I was not very clear on that. I know it's also while mumbling a little bit there. I'm sorry. So yeah, thanks for the opportunity to reiterate that. So first off, this one includes the B feed down still. And B feed down is at the RAA level 0.1, 0.15, something like this. So So B feet down, right? Which has nothing to do with J psi in medium physics, right? That's the first thing. There's a significant part from the B feet down still in there. What determines, so then you ask, why is it so strongly suppressed already at SPS? And that is what we now understand due to these very nice NA50 and NA60 measurements of J psi suppression in PA. And there's a large suppression in PA at relatively low energies, around 20 GeV or so. There's a very large dissociation of the J psi already in PA. That goes away as you go to high temperature, high collision energy. So actually, I thought I used to have a plot where I take out this what we call nuclear absorption. I'm not sure I have it, but it doesn't seem I have it. But you can, in principle, take out this cold. We call it the cold nuclear matter effect, right? If you take that out, then it looks more reasonable, and you see more clearly. You know, this will go up a lot, and on that new plot, and you see more clearly really the hot matter effect. If you were to take out the B feet down, you would really see that the primordial J psi would really have a strong decreasing trend due to that very hot quark-gluon plasma that you form as you go up in energy. But again, there are two things that mask this. One is the strong suppression from the PA at low energies, and at high energies, there's still this sort of plateau of B feet down, which is quite substantial, more than half of what is left here. Is that more or less clear now? Or?
Yeah.
Okay. Yeah. Thanks for bringing that up.
Okay, Santosh.
Yes, thank you. So very nice talk, and it's really interesting to see the ratio between the ds by eta by s. In one case, weakly coupled case, it is approaching the PQCD, and a strongly coupling case, it is approaching the ADS-CFT and then increasing. So at very high temperature, can we expect both will approach each other?
I would think so. Yes, I would think so. Maybe it's a slow approach, but maybe you never get there fully. But yeah, I would think so, because you know, the masses, yeah, the coupling, yeah, I think so, because you know, you also see it sort of from the spectral function, you know. At low momentum, at small temperature, the spectral function really smeared out, and it seems to be coming back at higher temperatures. And I would think that you know, the width maybe not changing all that much, but the quasi-particle masses probably go up. So yeah, I think it would approach it. It could be very slow though. Could be very slow, that approach though.
Okay, thank you. And another thing related to the same question. So similarly, in this DS case also, if we will also go to very high temperature, say, can we also expect both this weak and strong will give also the similar behavior as of this ratio?
Yeah, I would think so. Yeah, the DS is even more susceptible, I say, to. You see the DS, if you just look at the DS or the eta over S, the DS seems to have a stronger increase than the eta over S. So you would see, so the recovery of the weakly interacting QGP, let's say, would be, according to this, would be much more readily visible in the DS rather than the eta over S.
Okay, thank you. But I think suppose you will go to high momentum case, probably the recovery will even faster, is it? Yeah,
the high momentum, yeah, that's the next question. You know, these are zero momentum limits, these transport coefficients. And yeah, so I think that is something we can figure out from the RA of the mesons. You know, what is exactly the momentum dependence and how does it change with temperature? And as you know very well, that was a discussion we had at our workshop a couple months ago, right? And yeah, that's I think something we can and should get a handle on it, right? Because QCD will tell us there's an answer in QCD, and we should be able to find that answer with the help of our experimental colleagues.
Exactly. And it will be really interesting also to see at high temperature maybe how the will affecting. You have also recently done the radiative calculation. I was expecting few probably, but maybe it will also affect a bit in the.
Yeah, definitely. The radiative will come in there, and that's part of the challenge there. Yes, absolutely.
So thank you very much.
Thank you, Santosh.
Vedant,
Yeah.
just on this line, I would like to ask something.
Sure.
Yeah, hi Ralf, I am the PK Sau here. So on this basis, like the calculation of ds, you said that at zero momentum one can calculate, right? ds. But
Yeah, it's
again you have calculated for high momentum as well. So I would like to just maybe get clarification about that. How you relate the same parameter, both zero temperature and finite temperature. Sorry, zero momentum and finite momentum.
Yeah, that's
perturbative to non-perturbative.
Yeah, that's a very important question, and I think we don't have an answer to that yet. I mean, here's what we find in our current calculations, but we have also, we studied. We also know that the total strength of these calculations is not sufficient right now, because we are still in the phenomenology. If you really want to get a good agreement, we need a K factor still of like 1.5, which is unsatisfactory. So I think there is room for improvement in the momentum dependence here, and so that and whether this recovers a perturbative result, that again, I think it will be at rather high momentum. On the other hand, as also Santosh already remarked, at high momentum, you expect the radiative processes to come up, right?
Yeah.
So it's still, there's still a good amount of work to be done by the theorist, and certainly it will be aided by high precision data on the RAA and V2, the shape of those. Whether we can, for us to really get a more reliable calculations on the momentum dependence of this. Right now, it seems to have a pretty strong momentum dependence, but I'm not 100% sure whether this would be the final answer, because the phenomenology possibly has some problems with such a strong momentum dependence. We liked it originally, but because momentum dependence is running coupling in a way is the sort of the cornerstone of QCD, but maybe it's overdone here a little bit, I would suspect.
Okay. Because this is the gist of your talk actually. Basically, this DS is a very important parameter for measuring this QGP is that is existing or not. So I would say that this is a very important parameter.
Mm-hmm.
Yeah. Okay. Thank you for clarification.
Thank you.
Yeah.
I have one very quick question about this ratio, which you are talking about DS and eta by S. Now, experimentally, your tool is basically V2 and RA, right? Or is there anything else that will give you?
For DS, I mean, there are also for in the heavy, we have charm and bottom, and there are more sophisticated observables in the discussion, like correlation measurements, right? How the angular distribution, say, between a charm and an anti-charm diffuses if you go from PP to heavy ion collisions, or people discuss how the charm is deflected within a jet relative to the vacuum. So there are more sophisticated variables for the eta over and for the charm. The nice thing is, for the charm, we really have the full momentum dependence at our disposal, where the DS is really just quote unquote just the zero momentum limit, right? But experiment in theory has access to the full momentum dependence, which of this transport coefficient, right? The eta over S is of course what enormous amount of work went into from hydro extractions, right? And there it's not completely obvious to me what the momentum dependence is, but still, it's a huge challenge it was a huge work and challenge that where people have made tremendous progress to find even the thing, even the temperature dependence of this 8/s, right? And mostly, I think it comes in when you start deviating from the ideal behavior. So in the spectra, maybe around 1 GeV, when the V2 starts to turn over, that's usually when you say that's where the most sensitive to the 8/s. But it's a zero momentum coefficient, and from the hydro point of view, I don't think you have access to momentum dependencies of it. Okay. While for the heavy quark, you do.
Okay.
Yeah, that's right.
Okay, thank you.
Thank you.
Anirban, you have a question or?
Yeah, I mean, just if anyone doesn't have, then I'm.
Go ahead.
Thank you. I was wondering, I mean, recently there are efforts through the lattice-QCD also to really pin down the real and the imaginary part of the potential, not using free energy blindly anymore, but really the potential by which the wave function governed. Because
right.
So I'm wondering, I mean, in your two solutions now from the free energy data, which you call strongly and weakly, what is kind of the comparison if I compare with the lattice data at this stage now?
Yeah,
of those calculations which try to really separate out the real and imaginary part.
Right. So that is a very good question, and I followed that quite closely at the recent Strange Quark Matter conference, and there were lattice talks which really were sort of on both sides of the extreme.
Okay.
There was presentations which said all the J size completely melted already just above TC, and that really implies a very weak potential. And then there were other lattice talks which actually tried also to extract imaginary parts, and these imaginary parts were, the point was made, they are much larger than what you would get from perturbation theory, and also the real parts of the potential were much larger than what you get from the free energy. So I was very encouraged by those results, because personally I think the free energy, if that would be the potential, it would mean the imaginary parts are small. The potential is rather weak, and I think there's no chance to come up with a strongly coupled QGP if you would use that as your input interaction. So I was very encouraged by quite a number of lattice studies, which both in terms of correlation functions, but also in terms of extracting real and imaginary parts of potential, right? That now I think really going in the direction of very large imaginary parts and real parts which are well above the free energy.
Okay, because I mean, just one study I have in mind, not recently, because where you cannot, I mean, calculation of the screening masses in open and hidden charm mesons, where one has seen this sequential dissociation. I mean, you are increasing kind of the like SS bar channel, SC bar channel, and CC bar channel. So you see a sequential higher temperature of the dissociation, where of course you cannot talk about the deconfinement in a regular manner or formal manner, of course, but some dissociation. I mean, that's.
So I think what you mentioned is very reasonable. Actually, it's very reasonable, and I would be fully on board with those interpretations. Yeah.
Okay. Sorry, Ralf, I missed it. So you mean that the imaginary part is negligible, or?
No, quite the contrary. The imaginary part, there are a number of recent lattice calculations which find very large imaginary parts, much larger than you would expect from perturbative QCD like HTL or so. Much larger, and at the same time the real parts are also larger, and that really goes in the direction of what we would call the strongly coupled solution. And I'm very excited about that lattice QCD is also I don't know how to say it, but that they also find evidence for that, and quantitatively, even quantitatively, it's not far. So but I don't think we have the quantitative answer within our approach just yet. qualitatively, that lattice people are from their computations extracting large energy parts and potentials well above the free energy, I think is very encouraging for our general understanding of what these lattice observables, let's call them, tell us.
Okay. So you mean that there is some range of which real part will contribute to some range, like mu is a parameter, say lower mu and a higher mu or something like not in that. Is it like
mu with what do you mean by mu?
In chemical potential, like a higher chemical.
Yeah, chemical potential is another Pandora's box. I don't know. That's a very interesting question. That ultimately, you want to do neutron stars with it, right? I think at the moment, I think we are not in position to discuss the mu dependence really thoroughly, but before we reach some better consensus, which I think is emerging on the mu equals 0 axis.
Okay.
Okay.
Thank you very much for the discussion.
I think there was a very nice set of discussions. So I don't see any other questions. So then let's thank Ralf Rapp for this very nice talk, spending some time with the Alice India group and this lively discussions. So Ralf, thank you very much.
It was really a pleasure and honor to give this talk, and really inspiring discussions. Thank you for everybody. And thanks for listening.
Yeah, thank you.
Thank you. Thank you. Okay.
Bye.
Bye-bye.
Bye-bye.